This is lecture 15 on groups of order up to 8, which I've written this way. It's a part of the Pure Math course on finite group theory at junior and senior level, and Barnard is the first author of the text that I'm using, and here's the text. It's in the Teach Yourself series, and the title of the book is Mathematical Groups. You can find details of this book, how to buy it from Amazon.com, second-hand or new, or if you prefer in electronic form, download it from emule.com. For details, go to this website. So prof, short for professor, Hugo deGaris, that's my name, wordpress.com, and click on the tab deGarisMPC, MPC, Math, Physics and Computing, because this whole lecture series is mostly graduate level pure math and mathematical physics courses, or lecture sets as I call them. Alright, so today what we're going to do is to try to find all the various types of groups that one can have up to the order of the group being 8. And you'll see, well, you can you can see from here it gets pretty nitty-gritty, a lot of detailed logical reasoning in this lecture. So I'll ask you, to pay attention, put on your thinking caps. All right. So you may remember in earlier lectures that we asked the question and we proved a theorem on if you have two groups and you know they have the same order, and you're suspicious they are not isomorphic, they're different groups. So how do you go about proving that? And gave you a theorem on how, one suggestion on how to prove that two groups of the same order are not isomorphic, so they're different groups. So that may lead on to the question, well, for a given order of a group, how many different kinds of groups are there? Is there some theory that would allow us to classify the groups for a given order? So you give me a positive integer. Is it possible to classify all types, different types, non-isomorphic types of groups of that order? Now I think in general, I don't think that's been done. It's a huge challenge. Because even, well, later in this session, I will analyze for just of order 6. Now I'll do order 4 and some of the others. And in a later session I'll do order 8, which will just take up the whole board anyway. So as the order increases, it just gets more and more complicated and involved. So as yet there is no general classification of all types of groups, as far as I know, unless the classification of simple groups, but even then. I better plead ignorance on that one. I don't think there is a general classification of all types of groups. I need to think about that a bit more. If I'm wrong, I'll come back to you in a later lecture and tell you. Anyway, okay, so we're going to analyze the types of groups that can exist for groups of order up to and including 8. Right? That's what this lecture is about. All right? Now, the tools that we use to do this analysis, well, essentially two of them. One is actually a kind of corollary. Are you familiar with that term? A corollary. C-O-R-O-L-L-A-R-Y. Corollary. A corollary is just an immediate consequence, an immediate deduction from a main proof, a main theorem. So you prove something in your theorem, and then it's immediately obvious that some result can be derived from that, and so that result proof is called a corollary. So it's like a less important consequent proof of your main proof. So a corollary of theorem 48. Now 48 was the famous one, right? That was Lagrange's theorem, which says that the size of a subgroup divides the size of a group, or more technically, the order of a subgroup, because it's still a group, the order of a subgroup divides the order of the group. Okay. Now this corollary was that every member of that group, its order, so the order of the member, divides the order of the group. Okay, so that's 9. Now we'll use that. We'll use that corollary a lot, right? Here it states here. So little k here, that's the order of your element, x, and by definition, x to this power is just the unit, right? So, and this k here, the order of the element, divides the size of the group, the order of the group. Okay, so we'll use that, right? And another theorem we did previously was if your group, if its order is a prime number, so if you have a prime ordered group, that group is cyclic, right? And all groups isomorphic to it are cyclic. So effectively, there's just one group, right? And it's cyclic if the number's prime. All right. So here's the task for this lecture: is find all types, all non-isomorphic groups of order, up to and including 8, such that the size of the group is less or equal to 8. All right. Well, immediately let's get rid of the prime numbers, because that's the easiest case. From here, a prime ordered group is cyclic. Okay? So here your prime numbers less or equal to 8, 2, 3, 5, and 7. So these groups, the numbers down here, just I use that to represent their order, the number of elements they have, their size. Okay? So group 2, G3, G5, G7, these are all prime numbers, and therefore these 4 groups here are all cyclic. So let's label the cyclic group of order 2 as C2. Right? There's only one group that's has prime number order, and all the other groups of this order 2 are isomorphic to it. So effectively, it's just one group. Right? So call it the cyclic group order 2. So cyclic group order 3, 5, and 7. So you can write that in this form. So it's a cyclic group, remember. So it has a generator. P here is this number here. So P in general. So P for a prime. Okay. So the order is prime. So the members of this cyclic group will be of this form, where A is your generator, up to P to the minus 1. So you have P elements in your group. All right. So we've done now C1. I've been bothered with. It's so trivial. That's the trivial group. The only member is the unit, right? So strictly speaking, I could say G1, G2, G3. Already done. There's cyclic group, cyclic group. Now G4, that's what we'll talk about now. G5, that's a cyclic. G6, we'll do that later after we've done G4. G7 is cyclic. And G8, it requires a lot of analysis. That's why we're only going up as far as G8, order of 8. Because I'll fill a whole board on G8 alone, right? With dense reasons. It's even worse than all this stuff for G6, believe me. Yeah, that'll be a later session. All right. So we've eliminated 2, 3, 5, 7. That leaves 4 and 6 and 8. Right. So we'll do those systematically. So let's start with G4. So it's a group. And it has 4 elements. Its order is 4. The order of the group is 4. So it has 4 elements. Right? Now, using using Theorem 49, it means that each element, its order divides the order of the group. So the order of an element, each element will have its order, and that order divides G. Okay, so that will be our main tool. We will use that again and again. Right, so let little g just be any member of your group, so of G4. So its order by this theorem is 1 or 2 or 4. Okay, now if the order is 1, well then that element G has to be the unit, right? That's pretty trivial. So that's a subgroup, and that's the trivial subgroup. All groups have two trivial subgroups. The trivial group, the set of one element, the unit, and the group itself. Right? They're the two so-called improper subgroups. There are two improper subgroups. All right, so we can get rid of 1. So that leaves us with the order of this general element is 2 or 4. Now if it's 4, that's the size of the group. So that would make this G here